What is the axis title over here on the y-axis? Potential energy. And then here? Reaction progress, or you can put time. There's actually a number of axes in here. So it's going to start medium, go low. Where are you going to label? I'm going to put some letters on here. Where would you label the delta H here? Between what two letters? A and C. Good. So we're looking at the reactant energy and the product energy. And the difference between them is about that much right there. So that's my delta H. You guys said this was exo, and what sign do we associate with an exothermic process? Negative, so you can see there's a release of that much energy there. Okay, so we're going to add on to this just a little bit, and what you can do is you probably still have some space to work with. There's a quick video that I'll have you watch, just add some of the pieces that he's saying in the video, and then we'll conclude together on this piece. Can I move on to the video? Almost? Okay. There'll be another graph in the video, so that's why you're seeing it as secondary time anyhow, so I think you guys will be all right.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat, and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction. So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat, it's taking it from the surroundings, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place, so in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reactions. Now in the lab, we can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed. Now a really neat way to observe this is to use a model,
Okay, so under your endo and exo, kind of your two pieces, you've got a piece of place on the back of that flipbook. Make sure you put exothermic is releasing heat, endothermic is absorbing heat, and I'm going to add one more word to that, absorption. He said in the ice pack example, which is actually the one we read out yesterday, ammonium nitrate, it consumes energy. So that's why we say it absorbs energy, and then it gets cold. So we kind of know that taking in energy, consuming it, it means the energy is no longer there. So the lack of energy makes it feel cold. That's why an ice pack is an endothermic reaction. Opposite of that would be like a hot pack, which is the exothermic reaction, releases heat. So he said the temperature went up. This is the temperature went down. So you can add on to those couple of details to really help emphasize the energy transitions here. I'm gonna leave this up here. H gets cold. Excuse me? It gets cold. It gets cold.
A energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy than the products. Now where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products. And so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now this is a really intense reaction, and it's actually it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at the energy diagram of this over time as it progresses, we find that these reactants, the iron oxide and the aluminum, have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so we can see this as a downhill reaction. Now, what's going on? Why do we see this increase in energy here? Remember, we have to start pressuring those bonds, put a little bit of pressure on it before we can actually have them break apart, and we get that exothermic reaction. And we call that a activation energy. So you're going to put a little bit of energy into the system, but you can see that we're going to net energy coming out of that. And so that's going to be measured in heat coming off that thermite reaction. Now, if we look at an endothermic reaction, again, this would be like solid ammonium nitrate, and we're just combining it with water. So we're going to make ammonium and nitrate ions. In that case, what we're doing is the reactants are actually going to have a lower amount of energy than the products. And so you can see here's our activation energy, but this is an uphill reaction. In other words, it requires energy, it requires heat. Where is it getting for that heat? It's getting it from the surroundings. And so when we're measuring ectothermic or exothermic and endothermic reactions...
All right, so that's going to talk about AP Lab. You don't want that. You don't want it. Okay, so let's add one more piece to this. Make sure you have, and
what we're doing is we're explaining all reactions endo and exo. Graphically, why you guys just doing graph, but we're actually can also talk about them from a reaction standpoint. So turn back over your foldable to the lower right flap. So right here it says thermochemical equations BCE. Our graphical analysis, our graphical representation can also be a reaction representation. So this is a series of things I want underneath there, but it is a little repetitive because you just wrote down pieces of this. But specifically, I'm going to give you some examples in terms of Balanced equations, okay? Your top Grant, you with me, Grant? Okay. So for an endothermic reaction, you'll notice, and we actually have done this before back when we did entropy and enthalpy, we talked about the heat or energy being written in the reactant. So it could be like A plus B plus 100 kilojoules yields C plus D. So that's an example of an endothermic thermochemical equation. Where are you writing this now? On the inside of the flap of thermochemical equations. Good. So it can be written like this. Alternatively, this 100 kilojoules can be expressed on the outside of the products. So it could be like A plus B yields C plus D, and then just kind of away from the reaction a little bit, we'll put delta H equals positive 100 kilojoules. So this is one way of writing a thermochemical equation, and this is another way of writing that exact same thermochemical equation. Both of these are representing what type of reactions? Endothermic. Good. Okay. So can you guys use the same exact maybe setup, but modify it so it looks exo? Let's try to use the same system we have here, but make it an exothermic reaction.
Is the K there at the end of
Yeah, it's kind of like reaction, and then delta H is equal to positive 100 kilojoules. I ran out of space.
Oh.
So it's just kind of all this is to the side. This is 100 kilojoules.
Oh.
Yep. What do you guys think it was?
I thought it was B and then
Yeah.
I just
Okay.
So what's the bottom equation?
Hey, you're right over here. All right. It's around the space, but because we're not following. Okay, so A plus B plus 100 kilojoules yields C plus D. That's the first one. A plus B yields C plus D. Separate from the reaction, delta H equals a positive 100 kilojoules. That's it.
that's not good.
Huh?
So there's three equations.
No. So this, guys, this is the first equation. The energy is written as a reactant, showing the energy is going into the reaction as an endothermic process. Alternatively, you could also write it like this, showing that the overall process, yet again, is endothermic by the nature of here's the reaction, A plus B yields C plus D, but off to the side we wrote, hey, I'm positive, and this is the amount of energy that this reaction required. So we've seen these written actually both ways before when we talk about endothermic or entropy and enthalpy, but I'm just reminding you that endothermic means requires energy, therefore it's a positive value. We clear? Okay, so how would one write the same scenario but as an exothermic process? Tell me how you would write this right here.
A
Thank you.
plus B minus 100.
So I'm not going to write it, so if here it says write it in the reactants, this one says write it
Oh, okay.
in the product, so we're going to save that, okay? So yields,
C plus D minus 100 kilojoules.
we're still going to add it, because it's all, remember every time you write reactants, it's add, yields, add.
Okay.
So we're still going to put the 100 kilojoules as a product to show it's being released into the atmosphere or into the surroundings as just additional heat. So that's one way of writing it like we did it here. So how would I write it alternatively? Go for it, Austin.
A plus B yields C plus D of H equals -100.
Good, that's where we put the negative, because we're saying this enthalpy value is a negative value, negative 100 kilojoules, to express the nature of the reaction as exothermic. Do you remember a little bit, like, you remember seeing these?
I've never seen that in my life.
So, okay, what we did was we did like happy face, this is exothermic, sad face, this is endothermic. Do you remember happy faces and sad faces? Okay, so, well, I was looking at back at who did those. Some of you did not do those, so it makes sense why you did not see those. Okay, so the last piece of this is our relationship to the amount of stuff utilized in these reactions to make it endothermic or exothermic. So the amount of stuff means the moles. So what we have here is a balanced chemical equation. So for every 1 mole of A, it releases 100 kilojoules of energy. For every 1 mole of C produced, it releases 100 kilojoules of energy, and vice versa. For every 1 mole of B, it consumes or utilizes 100 kilojoules of energy. For every 1 mole of D produced, it consumes 100 kilojoules of energy. So what we can do is we can relate the coefficients to the delta H. It's so we can actually see if I have X amount of sugar, how much energy am I going to create through the combustion process of aerobic respiration. It does from the bottom. All right, thumbs up if you have that in your thermochemical equations. So everybody pull out your lecture notes real fast. It's on the back of your lecture notes from yesterday. I'm only going to do 1 or 2 per count for the rest, I think, are live. So from the back of PS 17. Yeah, that'll be fine. So, good question. For the picture for this flap of the foldable, you drew it on the back of your foldable, so you're good to go. Okay, so I just knew you would need more space. Alright, so everybody has the thermochemical equations and enthalpy values. Let's go ahead and label each of these as endo or exo. I just have to find this real fast, am I? Oh, it's right there. Ah, okay, so you found this. Give me a thumbs up. You found this. All right, so I want you to label 1 through 5 as endo or exo. Okay? Look at the delta H values, and then the last 2 you have to fill in the blanks so that it's positive or negative. You're also filling the blank on these. Think about what's happening in those processes. It has the sign. Okay, so this one, I think it's what process is that?
Oh, that's
but I'm going to them out first so you can read right on. All right, back to me. 3, 2, 1. Everybody, endo or exo, first one. Because it's negative, good. The second one, because it's positive. Next one, exo. Next one, endo. We're questioning ourselves, but I have a confident one over here. Tell me why. Okay, so this is low kinetic energy. So if this is like the cheat, if you forget like which is endo, which is exo, it went from a solid, which is low kinetic energy, to a which was what is liquid? Higher, but I'm gonna put medium kinetic energy. The only way you can increase kinetic energy is to add heat, right? So that's our endothermic process. So put a positive sign there. And then for the second one, everybody, because we're going from high kinetic energy to lower or medium kinetic energy, so it would be releasing that much energy. Okay, so I'm just going to do one of the thermochemical questions for now. So think about first what's happening. How much heat is lost or gained from the decomposition of 0.25 moles of sodium bicarbonate? So this problem is based on one of these 5 equations above. Which equation is it based on? 1, 2, 3, 4, 5. 2. How do you know that? Because this is the decomposition of sodium hydroxide, right? So decomposition of sodium bicarbonate, sorry. So all carbonates break down to make carbon dioxide. You guys can see that there. Will help there too. Okay, so in this case, is heat lost or is heat gained according to this reaction? Gain, because it's a positive number, so you'll circle gain there to make sure you're clear. And then there's one given, actually there's 2 givens. One given in this question and one given in the reaction above. What's the given in the question? 0.25 moles. Put 0.25 moles of sodium bicarbonate. Do a little dimensional analysis bar thing. Okay. So we're going to have to use the ratio, but in relationships with the heat, not just any old like product. Take care of the product. You'll notice this question is not asking about a product. This question is asking what? So what unit is it looking for? It's looking for joules or kilojoules, right? Because that's what heat is usually expressed in. So what we have up here is a balanced chemical equation. 2 sodium bicarbonates are decomposing, 2 moles of them are decomposing to make how much heat? I'm sorry, to gain how much heat? 129 kilojoules, right? So 2 moles use that much energy. So how am I going to figure out how much only 0.25 moles use? Okay, so I'm dividing and I'm... Right, so what's the ratio we're pulling, Austin?
0 to 129.
Right, so at 2 what?
At 2 moles.
Okay, so where do I put moles, top or bottom? Bottom, because I need to cancel. Good. 2 moles of sodium bicarbonate according to this reaction.
And 129 kilojoules.
Because according to this balanced equation, it consumes this much energy for every 2 moles. So you could probably have guessed it was going to be less. It's going to have like a quarter of a mole. But now from here, I'm going to calculate this, right? I was going to try to do this in my head, but you guys got this?
It's like 42.
Is that light or is it?
It's like 42.
Is it light or is it? I don't know if you calculated. Can you calculate?
It's 16.1.
Yeah,
I was so confident.
It was like 40 something. Okay, so 16.1 kilojoules. Okay. So what you can do is you can do dimensional analysis with a little bit of thermo in there as well. Okay? So we will utilize this a little bit more at the end of the class period.
Oh,
Okay?
that's it?
Yeah.
Okay, cool.
So that was a single stepper because we already had it in moles, right? And that's why we were able to use the moles here. If it started you with grams, you have to have a secondary step of taking grams to what? Moles and then moles to energy. So, I started you off with the easy one because that's how we always have to start. Okay, so I have a couple of things to request of you first. So thank you, Hannah just turned in some work to me. So park sports today, or like Tuesday and Wednesday, technically Wednesday. I just printed out your park sports. I got some people who are just lazy, just not turning work in. Unacceptable. I have some of you who are brilliant and you're great. Some of you guys were just absent and you just neglected to double check the website, turn some stuff in for me. So I have a couple people I need to talk to first before they go to the lab. So I need that just turned into a box if it's there. If it's not done, you gotta do that first before you jump in the lab, okay? So let me explain to you first what we're doing in the lab, because some of you guys will quickly progress to that, okay? So, before I tell you that, I'm going to leave this up here at the end of the class period, but on your problem set, look at your problem set now. So flip back, or no, yeah, flip over the paper. Write these values down, because it's not on your problem set. Do standard B. I don't have this on your problem set. And I told you one value yesterday just to assume with me, but this is the correct one today. So H diffusion of water, 6.01 kilojoules per mole. That is what we wrote down in our flowable yesterday. HVAP, I told you it's 44 just for the purposes to do problems yesterday, but this is the exact value. So 40.7. HVAP of methanol, 35.3 kilojoules per mole. And H diffusion of ammonia is 5.65 kilojoules per mole. If you don't write those down now, you just look them up in your book. Okay? So you'll use those for like some questions later on in the problem set. Yeah, that's why. Or take a picture real fast and explain our lab now, okay? Like I said, I'll put this back up there, but I was just making you aware that those data or those constants would be required to complete these questions. Yeah. All right, so for our lab, raise your hand if you brought something to burn. Okay, so we do have to group together to make sure we have enough folks in the lab at a time. We're going to go ahead, I'm just going to move past this for now, I'll come back to this. So when you get back to the lab, the first thing you're going to do is read and do pre-lab. Second, write your purpose, prep a data table, kind of normal stuff. You can't use the whole Cheeto, okay? You got to use like a quarter of the Cheeto. Don't use the whole thing because it'll take a while to burn, and I occasionally I might have to put the fire out because the fire gets too big. Okay, so it's like a small fire uses okay. Big fire, no good, and I will dump the DI water on it because I can't have it like set the fire off. Measurements should be very, very, very diligent because the small differences in masses or small differences in temperature will make a big impact on your values in the end. If you have time to do 2 trials for each food item, that's what I'm also saying to break it up. So if you need to do a second trial because your first was crap, you're able to do it again because you still have the same food item. Everything is kind of in the back. You will be setting up. This is the setup. You have like your ring stand. You have your aluminum can hovering like this far above the bottom of the ring stand. You're eventually going to put your thermometer in the aluminum can. Make sure your aluminum can is stable, not going to fall over first. And I have like a little paperclip food stand. If you have to manipulate it and kind of make it work so your food sits on top of it, because you don't want it to burn on the bottom. You have to stay standing in the air. That way also oxygen gets to it to help it as well. So I'll let you guys go back there in a second. Otherwise, we will be using matches to light. I have 1 lighter, and that's for the really difficult things to light. But matches will help you light. What's my rule of thumb for matches?
3 strikes. You're out.
That's for a striker.
Matches, get 1 strike. Put it in water.
Thank you. You don't blow it out because it smokes, right? Take the match, light it, drop it in here. Okay? So drop it in your beaker of water.
What's the stuff that goes up to the top?
What?
Like, if I put something, if I put like a burning match into the water, there's like
Phosphorus or something. Okay. All right. So, if I call your name, you're good to go to the back and get a group of 3. Okay. Nitty.
oh, I already got. I got.
Cole, Zoe, Savannah, Jasmine. Keep going. You're in a group of 3. Callie, Will, you're getting up and going to the back. Oh, I'm not talking right now. Thank you. Mackenzie, Vanessa, Nindika, Marissa, Anna, Aaron, Emma, and Olivia. You're good to go to the back. So you guys have all your work done in? Yep. You guys need to read the lab before you proceed. If your name is called now, please come to see me and come grab this for me.
Yes.
Annabelle, Pam, Zane, Anthony. Putting this into the box before you go to the lab. Hannah, Austin, Zane, come on down. Izzy, double checking somebody. Emily, Kelsey, guys, move to be speech up here. Luke, Nicole, Evan, Jacob. Evan. Austin, what?
Yeah.
Really minor. Evan, you have... Now, could you,
So are you doing all these now?
When did you? This one. No, you just turned your I just got that on the box. Looks like the outbox.
What does this look like? I'm pretty sure it's just me. What are we
I'm
talking
not,
about?
but I'm not accepting this where I didn't have it. You don't have it. So my website is
So I got
guys, sit down for me and I'll come to you. Go sit down. I just gotta keep this from the live first. Go sit down. I'll come to you in a second. All right, keep on the back. Keep on the front. I'll see what you're missing. I checked the logo off for you. Then get on the computer and see it. Same. So I don't. You just wait. I would have gotten it after 2 days. Okay, well let's do the video next first. Video next. You were asking one day, you just need to put some stuff in.
Okay, I got one. I'm just going to fail right now.
Okay, take a, get on my website, I'll show you what Anthony, what's your
Oh, that's fine. We did that meeting assignment when we get wait till the makeup assignment. Yes. I mean,
so that day we turned in the foldable and we turned in the 1 through 5.
I had done the 1 through 5, but then
I thought this was stuck together. I haven't graded this yet, but it was stuck together. No, I haven't graded it yet, but you're good. So otherwise, I think you turned it back.
Was this the sheet with the 1 through 5 on it?
Yep, it's down at the bottom. You might have watched some videos because you did not. You should have saw some of them. I already did 3 of the 5. I did them on video. I did 3 of the 5. Cam, do not work there. That's a lab station. Move back to your seat or get a computer. Move. Just log out.
I turned my course correction like this day after you brought it up.
Okay. Next. Get those done.
Can I burn this or
I don't think it'll.
it's gonna melt.
It's gonna get stuck with water.
Okay.
You put some box, please.
Oh, this computer's not working. Yeah, it says that the logon servers are down.
Are you doing this alone?
I'm wrapping the chips. Sure.
I'm sick. I feel like I'm being so sick.
I got you. Stick to that.
It's on the 13th.
Thank you.
Boy, how the hell do I 8-3 in Virginia?
That's the one I asked you.
Yeah, you got it.
Yeah.
No. Alright. Those I'm too good. I already I'm not doing this. You're what? You like it, bro.
There is no November 5th.
Wait, what's the constant?
Guys, make sure you look where your lights burn. I want to make sure you know we got correctly.
The point R. What's R?
6.